In the previous lesson, we took a look at some examples and gave a sort of rough way to compare topologies on the same blob. So now I'm actually going to show you how to build some new topological spaces out of old ones. And maybe just to remind you, since there hasn't been a slide on it, a space is just a set paired with a topology on that set. So here's a topology, and here's a blob or a set. Okay, now, of course, before I tell you how to make new spaces out of old spaces, let's actually just do this first for sets, just blobs. So you actually already know two ways of making new sets out of old ones. You would have seen this last week, the very first video of last week. If you have two sets, you can take their intersection, and you can also take their union. These are two ways of making new sets out of old ones. In this video, we're going to talk about sort of cousins of these operations. So the cousin of the intersection is called the product, or the Cartesian product. And the cousin of the union is called the disjoint union. Now, I actually don't really like this notation for disjoint union too much. It looks a little bit too much like the actual union symbol, though you will often see this in textbooks and papers and things like this. I actually prefer the sum symbol, and I hope that I can maybe convince you that this is the right symbol to be using for this operation, since it's not actually very much a union at all. Okay, so let's get started with the product, since actually the sum is defined in terms of the product. Okay, so a product of two sets is literally just the set of pairs from the two sets. So given two sets, say x and y, x cross y is the set, so here I'm going to use the curly braces notation, of all pairs xy such that x is in x and y is in y, like this. So if you're thinking of the xy plane or xy coordinates, that's exactly what's going on here. You should be thinking of the x and y as coordinates for a point in this space. So just as a quick example, if I take the set 0, and I take the set 1, and I take their product, this set has exactly one element. It's the pair 0, 1. And you should note that if x has, say, n elements, and y has m elements, then x times y has n times m elements. And this is exactly why it's called the product, because that's what it is. For sets, this is exactly what the product is. Okay, so let's actually look at an example, a slightly more complicated example. So this is our favorite example in the course so far. We've got the set 1, 2, and 3, and we've got the set dog, hat, and Angela. And I'm going to be using these brilliant pictures that Angela drew of a, well, okay, Angela didn't draw the dog. That's just a picture of a dog. But this is a hat, and this is a picture that Angela drew of herself. So like I said, the best way to think of the Cartesian product is actually just pairs of coordinates for points in the product. So I think it's very useful to actually draw a table. So on the left-hand side, I've got my 1, 2, and 3. And in the horizontal, we've got the dog, the hat, we've got Angela. So these points, these 9 points, okay, you should notice there are 9 because there's 3 points in this set and there's 3 points in this set. And so their product is going to have 3 times 3, which is 9 points. So these 9 points have coordinates that correspond to the horizontal and vertical parts of the table. So for example, this point right here is the pair of coordinates 2, Angela. And this point up here is the pair of 1 and hat. And if you can come up with the rest, then you certainly understand what actually a Cartesian product is supposed to be denoting. Okay, so maybe let's actually try looking at what the product of two spaces should be like, and maybe just take some guesses as to how this should go. So here's just an example topology on 1, 2, 3. There's the whole space, and then there's also the set just containing 2, and these are the 2 open sets in the topology, which are not empty. And down here we have the whole space, we have the dog and the hat as our 2 open sets, in addition to the empty set. Okay, so in the product topology, we actually have some choices. We can choose how to topologize this set, but here's my suggestion for how we should topologize this set. Okay, so I say, why not just take the open sets to be those sets which are in line with a set which is already open on one of the axes. And so, for example, this set should be open right here. These are the 3 points which are in line with this open set. So this should be an open set too. And there's a reason for making this choice, but right now you're just gonna have to bear with me and agree that this is probably the right choice. Okay, so what other open sets are there? Are there any other interesting open sets? Well, okay, so these 6 points are actually all in line with the dog and the hat. So maybe they should be an open set too. So I'm going to throw this in as an open set. And now at this point, you should notice that there are actually a couple of open sets which are not of this form if I want these 2 to be open. So in particular, the intersection of the 2 sets. So that's these 2 points right here. Doesn't include this one, and doesn't include these 4 on the outside. So this is not one of the strips that I was taking before. And that's why I've denoted it in purple. It's both blue and red, so it has to be purple or pink. It's hard for me to tell the difference. And there's also this larger open set, which is these 6 points, plus this one. So these are the union of the blue open set and the red open set. If it's hard for you to see, then maybe try drawing this on your own, and you'll see what I'm talking about. Okay, so in general, if we have 2 spaces, so here I'm going to call them xt and yt prime. These are 2 spaces. The product, so x times y, and you can write t times t prime if you really want, is the product topology. And this topology has basic open sets of the form U cross V, where U is in T and V is in T prime. So this is the general form of a basic open set in the product topology. This is the topology on the product of 2 spaces. U cross V. So what do these actually look like in the product of 1, 2, 3 and dog, hat, Angela? Could be good for you to go back to that slide and actually try to find all of the open sets of this form. You might recognize that they're actually these sets are actually intersections of the strips from the previous slide. And not all open sets are of this form. So this is of that form. This is the open set 2 crossed with the open set dog, hat. But the other set that we came up with, this one right here, is not a product of open sets. And in particular, it's because it's not a rectangle, right? So these 6 sets and this one are all in the set. So this set, this point right here, is kind of ruining the rectangle shape of this set. This is the union of the 2 strips, blue and red. Okay, so now let's talk about the sum or disjoint union of sets. I actually really like the word sum. I think it's very descriptive of what this operation is doing. Okay, so the basic idea behind the sum is to actually just put sets side by side. The sum is actually a very intuitive operation. It's something you've probably already done in this course and even before. So for example, the sum of this blob, which just consists of a dog, with itself. So here I'm taking a sum of this set with itself. This sum should have actually 2 points in it. So two dogs, in other words. I mean, 1 plus 1 is equal to 2. So this is not too foreign, right? Okay, but we need to be able to distinguish between the 2 points in a sum, because remember, we need to be able to distinguish between 2 points in the sum if they're going to be 2 distinct points. So we kind of need to give them colors, and this is what I've done here. You could color the left dog blue and the right dog green if you want, and that'll distinguish them. But because we're doing math, I would prefer to use numbers, and actually there's a payoff for using zeros and ones, and you'll see it in the exercises. So I've colored this left dog 0, and I've colored this right dog 1 by just putting them in a pair with their color. So this is how I've colored the dogs. Okay, so just taking these 2 new points, these 2 things which have coordinates 0 and 1 with the same dog, I'm just going to put them together into the same set. And I'm going to call this the sum of the blob consisting of the dog plus itself. So blob consisting of a dog plus blob consisting of a dog is just going to be 0 dog, 1 dog, like this. I mean, I don't know if I've done this yet, but this is exactly why I like this notation, because you get to add dogs to themselves, and that actually makes some sense mathematically. Okay, so what is the sum of sets in general? So the sum of 2 sets is, okay, well, remember the idea is to just put them side by side, label the left side with a 0, and label the right side with a 1. So if I'm given 2 sets, x and y, are sets, then x plus y should be, okay, so how do we label x with 0 and y with 1? You might want to pause and try to figure this out for yourself, because I'm just about to tell you. So I find the easiest way to do this would be to take the set containing 0 and take its Cartesian product with x. So this is the set of pairs, remember, of 0 and then x. This is meant to be a pointier bracket such that x is in x. So here I've just labeled all the points of x with 0. And I'm going to take the union of that set with 1 Cartesian product y, like this. And this is the set of all pairs of coordinates 1 y such that y is in y, like this. Okay, so just for a quick example, the set containing 0 plus the set containing 1 and 2, like this. I've got a 0 in here, so hopefully this isn't too confusing. This is going to be the set of 3 points, which is 0, 1, like this. And then 1, 1, and then 1, 2, like this. So in general, if x has n points and y has m points, then x plus y has n plus m points. And this is exactly why it's called a sum. And that's why I like to call it the sum, is that it satisfies this property down here. Okay, so let's take a look at a slightly more complicated example. Here I have our favorite set again, 1, 2, 3, or sets, sorry, and the other set is dog, cat, Angela. I've just put the pictures in here. Let's actually take the sum of these 2 sets. So again, a way that I like to think about this is just putting the sets side by side. So in this set over here, I have 3 points. And in this set over here, I have 3 points. The first one is a dog, hat, and Angela. And well, technically the one on the left, these points are all labeled 0, and these points are all labeled 1. These are, again, kind of coordinates, but really the purpose of the coordinates isn't to try to make rectangles or anything. It's just to put the sets actually side by side and distinguish them. Okay, so you can probably imagine how to give a topology to a sum of two spaces. You do exactly the thing that you do when you take the sum of two sets. You put them side by side. So here I've got the same topologies that we were thinking about back when we were thinking about products instead. So on the left, I've got the open set containing all 3 of the numbers, and then the open set containing 2, and that's just exactly this one right here, except I've got points in here instead of the numbers. Now, in order to get open sets in the disjoint union, or the sum of the two topologies, I basically just need to start taking unions of these two. So, for example, this set right here is going to be an open set in the disjoint union. Or even this set right here. This guy, the one that doesn't contain, just leaves out that 1 point in the bottom right-hand corner. So these are both open sets in the disjoint union topology. Okay, let's think about this more generally. So if X and T is a space, and Y and T prime is also a space, the sum topology, X plus Y, and if you want, T plus T prime, the sum topology consists of, it has open sets of the form U plus V, where U is in T and V is in T prime. Okay, and you can actually kind of ignore the whole basic open set thing in this example. We actually don't need these to be the basic open sets. These are actually just all the open sets are like this. It's one of those rare cases when we can describe all the open sets. So I'll just give you another example here. Say I have this space right here. This one's called the Sierpinski space. You saw it, I think, last week. And let's just take the sum of the Sierpinski space with itself. Just another simple example. Okay, so we've already kind of drawn a picture of this. It's just, maybe I'll call the left one over here blue. Whoops, that one was supposed to be blue. That's okay, it can be pink. And the other one is blue. Then the open sets are just, well, you take an open set over here, you take an open set over here, and you add them together. So for example, this is an open set. And since the empty set is in either, the open sets of this copy are also open in the sum. And conversely, since the empty set is open in the pink copy, then in the blue copy, all of the open sets from the original Sierpinski space are also open. And we can keep taking unions. Okay. So now you've seen a couple ways to build new examples of spaces out of old examples. There are a couple of exercises you want to try. You can find a link to them in the description. And I hope you make your way to the next video.